If Q stands for the set of all rational numbers, a set of x such that x equals p divided by q, where p and q are integers. Now p and q are integers, that means like 5 over 2, 7,348 over negative 5,963. Any number that we can write as an integer divided by an integer. Those would be all the fractions, greater than 1, less than 1, positive, negative. That would be the set of rational numbers. Now let's just see what the cardinality of the set of rationals is. First of all, 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so forth can be brought into one-to-one correspondence with the counting numbers 1, 2, 3, 4 in the obvious way. Just associate 1 with 1 over 1, 2 with 1 over 2, 3 with 1 over 3, and so forth. Now, so the cardinality of this set is the same as the cardinality of the counting numbers, which is all if null. Now, another thing is that all these numbers are rational numbers. And so this is a subset of the set of rational numbers, so it follows that the cardinality of the set of rational numbers can't be less than all if null. Right here is a set of rational numbers that has cardinality all if null. And if we add more rational numbers, that isn't going to decrease the cardinality. So that the cardinality of the set of rationals is at least all if null. Another thing we can think about is that 1 over 1, 2 over 2, or 1 over 2, 1 over 3, 1 over 4, all of these numbers are less than or equal to 1 and greater than 0. They get smaller and smaller, they approach 0, but they never reach it, and they get as big as 1. So that all these numbers are in the interval between 0 and 1 on the number line. Now there are lots of fractions in between these fractions here. For example, between 1/2 and 1/3 is 4/10. Between 1/2 and 1 is 3/4. And we can have infinitely many rational numbers in here. Any decimal number that terminates is a rational number. There are infinitely many of those in between any two of these numbers. And there are infinitely many of these. So it seems almost obvious that the cardinality of the rationals would be greater than all if null. Not only are there infinitely many of these between any two of these, but there are infinitely many intervals on the number line. And you have rational numbers filling every interval. They're dense along the number line. So it certainly seems like you should have more rationals than you have counting numbers. But that's not the case. And I'll prove it to you. Okay, we're going to list the rational numbers. Okay, right there is a list of all the rational numbers with numerator 1. Okay? Now I'm going to list all the rational numbers with numerator 2. Now you might say that 2 over 2 is the same as 1 over 1 and 2 over 4 is the same as 1/2. Maybe that's the case, but I don't care. I'm going to just list them anyway. I'm not going to throw any of them out. And I'm going to show that even if we include things that seem to be the same as others, this is still going to have the same cardinality as the counting numbers. Now what I've listed here in this row is the set of all rational numbers whose numerator is 2. And then we'll list the set that has numerator 3. And the set that has numerator 4. Okay. Now it seems that these columns will go on forever. Like this first column is a set of all rational numbers whose denominator is 1. Here are all the rational numbers whose denominator is 2, and so forth. Now if we follow all these dots and list all these out, of course we can't because there are infinitely many of them and we don't have that much time. But if we could, we would eventually, somewhere in this array, reach any rational number you might want to specify. Any one at all. It's in here somewhere. And if we make the array big enough, we'll find it. Now I'm going to number these in such a way that you can be sure that we're going to have a number, a counting number, that goes with every rational number. And here's my numbering. This is number 1. This is number 2. Now you might think that this is number 3, 4, 5, 6, but I'd use up all of my counting numbers just following this row, wouldn't I? Because this row never ends. I have a counting number for every number in this row. So I'm going to put number 3 down here. Now where am I going to go for number 4? Am I going to start following this row? Nope. I'm going to come up here, and I'm going to number 4, 5, and 6 here. Then I'm going to number 7, 8, 9, and 10 here. Now if I keep this up, I can take this table out as far as I want to, and I'll always have a number to go with every rational number, won't I? Okay, there's no end to how far I can go with this. Every rational number is going to appear in this table, and every rational number is then going to have a number that goes with it, because we're moving down the table in this direction, taking the whole thing and sweeping it out in this direction. We're going to reach every rational number by this method. So our conclusion is that the cardinality of the rational numbers is indeed Aleph null.